So we are solving the problems on Bodeplot. Let us take the next problem. So we have GH of S is equal to S into 1 plus S by 10 whole square, 1 plus S by 50 whole cube, and 1 plus S by 200 whole power 4, and in the denominator we have 1 plus S by 2, 1 plus S by 20, 1 plus S by 100 whole cube. Also we take one more, 1 plus S by 500 whole power 4. So this is the transfer function given to me. Now I have to draw the Bodeplot for this. So first of all, let me consider the magnitude plot. So we will take here only those frequencies which are given over here in the problem. So 0.1, 1, next we have so we have 0.1, we'll start with 0.1, then I'll consider 2. So actually before 2 I should take 1 also. So 1, 2, then I have 10, 20, 50, 100, 200 and 500. So we observe that we have a pole at 0. In this given transfer function we have a 0 at origin. So whenever 0 is there, it will give me a slope of 20 ndB per decade, plus 20 ndB per decade. So I have to start from minus 20. So I have to start from minus 20. I have to extend it to up to 1, and then it will extend it up to 2. At 2, 2 is the next corner frequency. At 2 we have a pole. So this will become straight line because here I had a slope of plus 20 dB per decade, and when I add a pole here it will become 0 dB per decade. Then at 10 what do we have? So let us not write this, it is quite clear that it is 0 dB per decade. Okay, next at 10 I have 2 zeros, so it will give me a slope of plus 40 dB per decade. Then again at 20 I am adding 2 more poles, so it will make it 0. The slope will become 0 again. At 100 I have 3 poles again. Sorry. Yes. So before that at 50 I have 3 zeros. So it will be plus 60 dB per decade. Then 100, at 100 I have 3 poles again. So it will cancel out slope. So slope will be 0 again. At 200 I have 4 zeros. So it will give me 80. And at 500 again I have 4 zeros. So this is how the Bodeplot is, plus 80 dB per decade. So this is the magnitude plot. Now there is no K here, so there will not be any shift. Next we will plot the phase plot. Now initially I have minus 90 because plus 90 because of 0. So it will start with 90, then it will become 0, then at 10 we have plus 180, again it will become 0, again we have plus 3 plus, so it's 90, 180, 270, and it will keep on increasing. So we have 360 and again 0. So 360 degrees. So this is my phase versus frequency. Now this is asymptotic plot. So the approximate exact plot can be plotted by considering the midpoints. And now I'll connect all the midpoints. So this way, this is the exact plot. So in this way it is very easy to draw the Bodeplot if the transfer function is given to me. Now there are certain things which has to be found, like first is change in scope. So let me consider a few questions. So in the above Bodeplot, what I have to do? A, find the change in slope first at omega equal to 2, omega equal to 10, omega equal to 2, omega equal to 10, omega equal to 20, omega equal to 50, omega equal to 100, omega equal to 200, and so on. So you can do it. So how will you find the change in slope? So we have seen that the change in slope occurs because if you add a pole or a zero at that particular corner frequency, that much slope will be changed. So in order to answer this question, you can directly observe in the transfer function itself. So you observe here that at omega equal to 2, we have a pole. So therefore the answer for this will be minus 20 dB per decade. So this much change in slope will occur, minus 20 dB per decade. Or from the Bodeplot also you can find it. So at omega equal to 2, we observe here that the slope is actually change in slope is found by taking the new slope minus previous slope. So new slope is 0 and the previous slope is plus 20. So if you subtract them, you will get minus 20 dB per decade. So actually we need not go into the Bodeplot. Without drawing the Bodeplot itself, we can answer these questions. At omega equal to 10, we observe that there are two zeros. So the answer will be plus 40 dB per decade. For omega equal to 20, we observe that there are two poles. So it will give me minus 40 dB per decade. So in this way you can answer all the questions. It's my plus 60 dB per decade. So this is how. Next. So second thing is find the slope at the following corner frequencies. Between the find the slope between the following corner frequencies. So first is between 2 and 10. Second is between 50 to 100. It also and third, let us take 100 to 200. So we have to find the change, we have to find the slope between these lines. Now this can also be done from the transfer function itself. So how will you do this? So while calculating the slope between any line, what you have to do is, now here you have to consider greater than 2 and less than 10. So therefore, what you will do is, you will include all the slope, all the poles and zeros. You will calculate all the poles and zeros up to the corner frequency 2, and then you will calculate the poles and zeros up to 10. So what we will do is, we will calculate all the poles and zeros up to 10 here directly. While calculating that, you will include this pole also, this pole or zero, and you will not include this. So this will be included. So what I am telling you is that observe the transfer function. If you observe the transfer function, we have up to 2. So we have to calculate the number of poles and zeros up to 10. I have to calculate the number of poles and zeros up to the corner frequency 10. So while calculating the frequency up to 10, I have to exclude the term exclude this term also, but I have to include this term, but I have to exclude this term. So if you observe the transfer function, in transfer function, the poles and zeros up to 10 are, so number of poles and zeros are, so we have a 0 at origin. So there is 1 0, and also I have one pole. So there is one pole at omega equal to 2. So 0 will give me plus 20 dB per decade, and pole will give me minus 20 dB per decade. So the overall slope will be 0. So 0 poles or zeros. So therefore the slope will be 0 dB per decade. So now you observe the Bodeplot between 2 and 10. The change is the slope is 0 dB per decade. So our answer is correct. Now let us find the slope between 50 and 100. So you observe here, while calculating this, you will find the number of poles and zeros up to 100. You will not include this. You will exclude 100. So less than 100. So you will exclude this. Excluding 100. So we observe here that we have 6 zeros. One is 0 at origin, two zeros at 10, and 3 zeros at 50 from the transfer function. Then now let me calculate the poles. So poles are 3 because I have not included 100. So excluding 100, there are 3 poles. So net effective will be 3 zeros, because 3 zeros will cancel 3 poles and 3 zeros will left out, and the overall slope will be 60 dB per decade from this. Similarly, you can find between 100 and 200. So you have to calculate the number of poles and zeros up to 200, and you should not include 200. So up to 200 we have 6 zeros and 6 poles. So it will be 0 dB per decade. So I hope this is clear. So whenever you have to find the slope between corner frequencies, so you will find the number of poles and zeros up to the highest corner frequency. Okay, this was the second type of problem. Then we'll find the next is C. So C is find the slope around the following corner frequency. So omega equal to 2, 20, is 20 there? Yes, 20 is there. So 20, 200. Okay, so we have to find the change in slope here. Slope around the corner frequency. That is, before 2, how much is the slope, and after 2, how much is the slope. So in order to find this, so let me take around 2. So while taking around 2, so you have to calculate 2 slopes here. So around 2, so one is less than 2 and one is greater than 2. So what is the slope for the line which is less than 2, and what is the slope for the line which is greater than 2? So while calculating the slope for less than 2, you will exclude the number of poles and zeros at omega equal to 2. So you will exclude while calculating for less than 2, and you will include while calculating for greater than 2, because it will affect. Now if you observe here, up to 2 we have only 1 0. So 1 0. So it will give me a slope of 20 dB per decade. So for the less than 2 we have 20 dB per decade slope. For greater than 2 we have 1 0 and 1 pole. So it will cancel each other and you will have 0 dB per decade. Similarly, let me take one more example around 20 suppose. So around 20 what will happen? So around 20, so less than 20 and greater than 20. So here we will exclude this and here we will include this. So for less than 20 we will exclude 20. So we have 3 zeros and 1 pole. So overall we have 2 zeros, which will give me a slope of 40 dB per decade. Then for greater than 20 I have to include 20 also. So 3 zeros and 3 poles. This will give me 0 dB per decade. So in this way we can find the slope around the corner frequency. In this case we'll get two slopes. So I hope all these things are clear. So it is very easy to draw the Bodeplot if the transfer function is given to me. Next we will consider the inverse Bodeplot. This is very important. Inverse plot is more important when compared to the forward plot, because most often the question is being asked from this topic. Rarely the question is being asked from the forward plot. Mostly the question asked is from inverse plot, and this is more important. Consider the inverse plot. So in inverse plot there will be a Bodeplot given to you, and from that we have to determine the transfer function of the system. So for example, let me consider this. Find the transfer function to the given magnitude plot. So this is the transfer function This is the plot given to me. So this is 5, 10, 2.1 plus 40. This is also plus 40. Okay. So this is plus 80 dB per decade. This is minus 60 dB per decade. Okay. This particular line is 0.1. This point is 0.1. 0 dB magnitude in dB, and this. Okay. So now from this given Bodeplot, we have to determine the transfer function. So how will I determine the transfer function? So there are certain steps. There is a procedure, steps. First step is we have to observe the initial slope. Second step is, okay, so initial slope will give me, this will give me poles and zeros at origin. It should be or actually, because poles or zeros will not get both. So poles, so if the initial slope is negative, then we will get poles. If the initial slope is positive, then we will get zeros. Then second is find the change in slope at each and every corner frequency. So you will find the change in slope at each and every corner frequency. If the change is positive, then finite zeros at that corner frequency. And if the change is negative, then finite poles at that corner frequency. So first step is you will observe the initial slope. Second step is you will calculate the slope at each and every corner frequency. Then third step is to find the value of k. So third step is find the k value by using known magnitude at known frequency. So these are the steps. Now we will solve. So let us apply these steps to the given problem. So if you observe the diagram, now I can, so I have the diagram with me. You also to keep drawing the diagrams in your notebook and verify this. So the first step here is we'll consider the initial slope. So initial slope is 0 here. There is so no slope at initial. So therefore this implies no poles or zeros at origin. No poles or zeros at origin. This is one's first step. Now second step is the calculation of change in slope. So change in slope at omega equal to 2 is, so at omega equal to 2 the change in slope is, so change in slope can be direct, so you can observe here that at 2, so after 2 there is minus 60 dB, so minus 60 minus 0, it comes out to be minus 60 dB per decade. Then we'll calculate change in slope at omega equal to 5. So at omega equal to 5 the change in slope is, it's 80 minus of minus 60, it comes out to be 140 dB per decade. Then we'll calculate change in slope at omega equal to 10. So we have 0 minus 80, so it's minus 80 dB per decade. So we have got the change in slope for all the corner frequencies. Now I can write the transfer function directly. So transfer function is k into, we'll keep k as it is and then we will find the value of k. So initial slope is not there, so we do not have any pole at and 0 at origin. Now at omega equal to 2 the change in slope is negative, and change in slope is negative implies that there are poles at that particular corner frequency. So we have 1 plus s by 2 whole power 3. Why 3? Because one pole will give me a slope of minus 20 dB, so it is minus 60, so it must be 3. Okay. Next, at omega equal to 5 I have 7 zeros, so 1 plus s by 5 whole power 7. Then at omega equal to 10 I have 4 poles, so 1 plus s by 10 whole power 4. So this is the overall transfer function of this. Now we have to determine the value of k. So k value is determined from by considering the known magnitude at a given frequency. So if you observe the Bodeplot, you will observe that you will find that at omega equal to 0.1, at omega equal to 0.1 the magnitude is plus 40 dB. So at omega equal to 0.1 the magnitude is plus 40 dB. Now we will apply this condition. So what we will do is we will calculate the magnitude of this. So if I calculate the magnitude of the transfer function, it's 20 log k, directly in dB I am calculating, plus, okay, let me write it in the order of corner frequencies, increasing order of corner frequencies. So minus 60 log of under root of 1 plus omega by 2 whole square plus 140 log of under root of 1 plus omega by 5 whole square and minus 80 log of under root of 1 plus omega by 10 whole square. So these are the magnitudes. Now at omega equal to 0.1 what will happen if you approximate it? So at omega equal to 0.1 this term will become approximately 0. So this term will be cancelled out to 0, this term will also be cancelled out to 0, this term will also be cancelled out to 0. It is in the same way as we have done in the approximations earlier. Now at omega equal to 0.1 we have given that it is 40. So I'll write here at, so this we have neglected these slopes, these magnitudes, because we are considering at omega equal to 0.1. So therefore 40 is equal to 20 log k, and k will come out to be 10 to the power 2, which is 100. So at omega equal to 0.1, these all will be less than 1. Omega by 2 will be less than, very much less than 1. Omega by 5 will be very much less than 1. And omega by 10 will be very much less than 1. So these all will be log 1, log 1, log 1. All of them will become 0. So therefore k is equal to 100. So the overall transfer function will be the same one with k equal to 100. So in this way we can calculate the transfer function from a given Bodeplot. Let us consider one more example. So every year a question is being asked in the gate from this topic. So please practice many, take many Bodeplots and keep on practicing this. It is very important from gate point of view. So the question is, this is 10, this is 5, 2, this is minus 80, magnitude in dB, slopes are given to me minus 80 dB per decade, and here I have 100 dB per decade. Okay. Now again a Bodeplot is given to me and I have to determine the value of transfer function. Okay. So again we will start with, so here we have initial slope. So initial slope is equal to minus 80 dB per decade. So this will give me 4 poles at origin. So we have 4 poles at origin. At 5 the change in slope is, at omega equal to 5, change in slope is equal to, how much is the change? It's 0 minus of minus 80. So it's plus 80 dB per decade. Then at omega equal to 10, change in slope is equal to 100 dB per decade. So now we can write the transfer function directly. So the transfer function will be k into, we have at omega equal to so at origin we have 4 poles. So I have s power 4. Then at omega equal to 5 we have again, so if you observe here the change in slope is positive. So here we have 1 plus s by 5 whole power 4 into 1 plus s by 10 whole power 5. So this is the overall transfer function. Now here we have to find the value of k. If you observe the Bodeplot, we find that the magnitude here is not given. The magnitude at omega equal to 0.1 is not given to me here. So therefore I have to use the magnitude at some other frequency. Here I know that at omega equal to 2, the magnitude is 0. So let us make use of this. So first of all I will calculate the magnitude of this. So magnitude in dB will be equal to 20 log k plus, this will be 80 log of under root 1 plus omega by 5 whole square plus 100 log of under root 1 plus omega by 10 whole square, and we have minus 80 log of omega. So these are the magnitudes. Now we have omega equal to 2 here. So at omega equal to 2, magnitude is equal to 0 dB. So we will apply this condition. So this will be 0 is equal to, this will not get cancelled. So this will remain as it is, 20 log k. This is 80. So this will get cancelled because omega by 5 will become very much small than 1 at omega equal to 2. So this will be cancelled to 0. This will also be cancelled to 0. Again, this will not be cancelled because this is less than 2. So log 2. So therefore we have minus 80 log 2 here. So this comes out to be log k is equal to, if we divide this, we'll get 4 log 2. So this implies k is equal to 2 to the power 4, which is 16. So this is the method to solve this kind of problems. These are very important, so please pay special attention to this. Next we will study the concept of gain margin and phase margin. They are really important, and the question is being regularly asked from that. So next topic would be phase margin and gain margin. So actually phase margin and gain margin are used to determine the stability from the Bodeplot. So again we'll keep the heading as stability here, stability from Bodeplot. Without using Bodeplot also you can determine the values of phase margin and gain margin. Okay. Now you know that we have been considering this, that 1 plus g of s into h of s. This is nothing but characteristic equation. This is nothing but characteristic equation. So from this I get g of s into h of s is equal to minus 1. We have already considered this earlier. Now replace, if I replace s by j omega, I'll get g of j omega into h of j omega is equal to minus 1 plus j0. Now from this again we'll get the two conditions as we have done in um, in the previous chapter, root locus. We have already done this. So now if I find the magnitude condition, so mod of g of j omega into h of j omega comes out to be 1 in linear scale, and magnitude in dB is 0. So the frequency at which this happens, the frequency at which the magnitude is 1 in linear scale and it is 0 in dB scale, is called as the gain crossover frequency. So we are going to define a term called gain crossover frequency, which is called as omega GC. So the frequency at which the magnitude is equal to 1 in linear scale and 0 in dB is called omega GC. This is from magnitude condition. Now if you apply the angle condition, So angle of g of j omega into h of j omega is equal to angle of minus 1 plus j0. So we have uh, considered this to be minus plus 180 degree, plus minus 180 degree. But here we will consider only minus 180 degree. So the reason behind this is that always we consider a system with poles greater than zeros, and poles will give me the negative angle. So therefore we always consider the minus 180 degree. Now the frequency at which the phase becomes minus 180 degree is called as the phase crossover frequency. So we are going to define one more very important term, phase crossover frequency, omega pc. So the frequency at which the phase angle is minus 180 degree, the phase angle is minus 180 degree, is called omega pc, phase crossover frequency. So we have defined two frequencies, one is omega gain crossover frequency and the other as phase crossover frequency at two different from the magnitude condition and the angle condition respectively. Fine. Now we will define the terms called gain margin and phase margin. So gain margin is nothing but gain margin is equal to 1 by magnitude in dV at omega equal to omega pc, which is equal to 1 by magnitude of g of j omega into h of j omega at omega equal to omega pc. This is in linear scale, and if you consider gain margin in dB, this will be minus 20 log of mod of g of j omega into h of j omega at omega equal to omega pc. So this is the definition of gain margin. Next, similarly, we define the term called phase margin. So phase margin is 180 degree plus angle of GH at omega equal to omega GC. So what we will do is, first of all, we have to calculate the angle at omega equal to omega GC, gain crossover frequency. So angle at gain crossover frequency, and then add it to 180 degrees. So that is phase margin. So these are the definitions of gain margin and phase margin. Now, depending on the gain margin and phase margin and the positions of gain crossover frequency and phase crossover frequency, we can define the stability of a system. So there are cases over here. So first is when omega pc is greater than omega gc. In this case, the system is stable and gain margin is positive, phase margin is also positive. Both will be positive, gain margin as well as phase margin. So gain margin is positive in decibels actually. Next, when omega pc is equal to omega gc, the system is marginally stable. So in this case, gain margin is equal to 0 dB and phase margin is also equal to 0 degrees. And when omega pc is less than omega gc, the system is unstable. Here gain margin is negative in decibels and phase margin is negative. So these are the concepts of gain margin and phase margin. So by using gain margin and phase margin, we can determine the stability also. So this is all about Bodeplot. Now next we'll move on to the polar plots and Nyquist plot. Polar plot, actually we'll see polar plot and Nyquist plot, we'll discuss there itself.